So it's my pleasure to introduce Brandon Lucia, who's a professor at CMU, and he's going to talk about intermittent computer systems in space.
All right. Yeah, Mike, thanks for the introduction. It's great to be here. I do wish I knew how many of you were here, and I do wish that I could see you all in person, but I guess this will do for this year, and we can try this again next year or something. I am here to talk about my lab's work on the field of intermittent computer systems. I'm going to go through some background on what intermittent computer systems are, and then I'm going to talk about applications of our work on intermittent computing systems to space-based computer systems, including some work on small satellites that we've been doing. I wanted up front to just give credit to everyone that has been part of the work that we're doing. This list of names grows every year, and it makes me very happy that it does. So just wanted to give credit where credit's due to everyone that has worked with me on this work. Okay, so the premise of what I'm going to be talking about today, in the context of today's talk, we're focusing on space. And so the premise is that tiny satellites are really just tiny computer systems. And they're very interestingly constrained tiny computer systems. They're interestingly constrained because they have to be small. They have to be lightweight because when you launch something into space, you sort of pay by the ounce. So you need things to be very small and very lightweight. And being very small and very lightweight limits the amount of capability that you can cram into a box. And on the right side of the slide, you see a sort of artist's rendering of a CubeSat in orbit. And on the left side of the screen, you can see an image of a whole bunch of chipsats being kicked out of a CubeSat. Chipsats are one of the platforms that we developed. We have been developing chipsat form factor satellites. I'll talk more about those later. But one of the key things that you'll notice about these is that because they're so small, they're also quite limited in the amount of power that they have to use. They're just using these tiny solar panels. So I'm going to talk today about how that is a really fundamental requirement if we want to do useful computing on these devices. Often, when we think of small embedded computer systems, and here's a smattering of small embedded computer systems, only some of which operate in space, like the one at the top of the slide in the center, they're often tethered to a power source. So you strap a battery to this thing, and then it runs reliably and continuously over a long period of time. And once in a while, you have to go and switch the battery out. Being tethered to a power source, though, is a pretty big impediment if you want to launch something into space. And so there's a lot of issues with that. To native batteries. Batteries are heavy, so they increase the cost to launch. But batteries are also fragile and not very robust to temperature. And so being tethered to a power source like this is really an impediment in general for embedded computer systems, and in particular for space-based computer systems. So our goal is to get rid of the need to be tethered to a power source like a battery. We have been taking advantage of a technology that has been maturing over the last 10 years to a point where it's becoming fairly usable, that is called energy harvesting. Energy harvesting is a way of untethering a device from its power source. What I mean by untethering is that we eliminate the need to have a large battery, and we replace having a large battery with a series of other components that play the same role. So at the top of the slide, you can see my lab's Capybara intermittent embedded computing platform. There's a lot of components on this board, and I'll talk about some of them later, but the ones that are relevant to the idea of energy harvesting are that we have an energy receiver. This is like the solar panel that I'm pointing to on the slide here. We have an energy buffer, and in our case, this is an array of small capacitors. And capacitors store a small amount of energy, but they're much smaller and much lighter and have much lower capacity than energy capacity than a battery. We also have a computer on board here. In this case, it's a microcontroller. And so if you put all these things together, you can collect some energy, put the energy into the energy buffer, and you can run the microcontroller. And that means you can do useful computation, you can access sensors, and you can activate radios to send messages. At the bottom of the slide, there's another form factor of energy harvesting computer system. You can see on the left side of the slide, there is an RFID reader that's marked as energy source. And on the right side of the slide, there is a rat's nest of wires plugged into a breadboard. And this is the very first energy harvesting system that I ever built on a breadboard. And it runs an experimental microcontroller board. I like to include that because there's really not a lot of mystery or magic to energy harvesting systems. You can make them with a kind of rudimentary collection of components. So we want to send these into space, and energy harvesting will let us do that. We can get rid of the batteries, and it's easy. We just put a bunch of small devices with embedded sensors and radios inside of a launch vehicle like the CubeSat that you can see here, and we can fling this into space, and we'll have a new kind of space mission. And this will be trivially possible. Obviously, this is not the case. There's more complexity to the story here. If we want to take a bunch of small embedded computer systems like the ones that you see here and launch them into space, there are other problems that we need to solve once we move to a world where we're using energy harvesting. The problems that I'm going to talk about today are in particular related to the fact that energy collection in an energy harvesting system is intermittent. You can only use energy when there's energy in the environment to collect, and you can only buffer a small amount of energy in the capacitor on board. And so periodically, because the energy is intermittent, the system experiences power failures. And because of these power failures and the fact that they can happen essentially at an arbitrary point in time, software becomes inherently unreliable. Software does not expect the power to be turning off all the time when energy in an environment is intermittent. And so today I'm going to talk to you about the intermittent execution model, and I'm going to give you a way to think about intermittently powered devices that work with energy harvesting. I'm going to talk about a couple of our system designs that we've built, primarily software system designs that enable reliable intermittent computing, despite the fact that the power in the environment may not be continuously available. And last, I'm going to talk about applications to space systems in particular. So the gist with intermittent computing, this is just a high-level picture of an intermittent computer system. On the left side of the slide, you can see a picture of a ChipSat satellite platform that we developed in my lab. The vital statistics are listed here. We need a few milliwatts of power to run the CPU microcontroller chip. We need some power in the tens or hundreds of milliwatts to run the radio, and sensors have a wide range of power consumption. The harvestable power, though, is on the high side around 10 milliwatts, and so we can't run all of this stuff just straight off of the solar panel. We need to buffer up some energy if we want to run these components. So on the right side of the slide, you can see a time series that shows the available energy over time. And you can see for part of this curve, the yellow part of the curve, we're slowly charging up, and then the device hits what we call the lifeline, where enough energy has accumulated, say you filled up your capacitor bank, that you can do some useful unit of work, and then you operate for the duration of this time series that's indicated by the green line. This is notional, this is not actual data, and the yellow part of the curve should actually have a much shallower slope to it, and the green part of the curve typically is quite steep, because the energy available in the environment to very small solar panels, like I'm showing here, is low. That's typically a very low power input. And the power consumption can be quite high, and so we can use up that energy very quickly. At some point, we use up all the energy and we hit the death line, and when we get there, that means the system has to turn off. And if there's no more energy to collect, then the system just stays powered off. Eventually, we might get more energy, we can recharge, and then continue kind of executing through this cycle of charging up and then running in a burst of activity. This is intermittent operation in a nutshell. So we've abstracted the kind of low-level behavior of the system away. You're looking at this low-level behavior where energy is varying over time, and the system is powering off and powering on, and there's sort of very system-dependent parameters built into this, like the amount of energy that we can buffer and the power in the environment. We want to get rid of some of those details, and one simplifying thing that we can do to think about an energy harvesting system and intermittent execution is to not think about the continuous variation over time of the amount of energy in the system, and instead to just think about periods of computing sort of interspersed with periods where the system is rebooting, where we lose power. And that's what I'm showing here with these green and red rectangles. During the green rectangles, we're operating, and during the red rectangles, the system is just powered off and can't do anything. And our goal is to make programs run reliably on a system, but the programs should span longer than one of the green boxes in this time series. And if we do that, then we have what we refer to as the intermittent execution model for software on an energy harvesting system. And the key distinction between the intermittent execution model and the alternative, which is the continuously powered execution model, is that in the intermittent execution model, we assume that failures are part of the execution. So in a continuous execution, a continuously powered execution, a failure is a catastrophic event. And when that happens, everything sort of resets and you start a new execution. In the intermittent execution model, the failure is part of the execution. And so we design the system to expect it. So let's see what happens if we just take some software and naively run it with the intermittent execution model. This program is pretty simple. We're just going to put a bunch of characters into a buffer. So we're going to call this append function a few times, and we're going to fill up the buffer. We're going to just bump a pointer and then put a character into the position in the array indicated by the pointer. Size is the pointer there. So we can take this code and try and run it, and we'll very quickly see that if we can't get through the whole program, we might get through a few loop iterations here and there. Maybe some of these execution periods are a bit longer because there's more power in the environment available for the system to collect energy at a higher rate. But we don't really get very far. This software wasn't written to work in an environment where we're powering off every 10 or 50 or 500 milliseconds or whatever it's going to take. So unless we can finish this entire computation in one shot, this code is not appropriate for use in an intermittently executing device that's an energy harvesting device in the way that I've described. And so we can look at this intermittence property as a control flow problem. So this is the same program that I just showed you a second ago, and we're looking at it now as a control flow graph, just so we can kind of think about it in a little bit more of a principled way. And the way that we can think about intermittence as a control flow problem is that from any point in your program, execution may non-deterministically jump back to the entry point of the program. So we just go back in time every time there's a reboot. And that's reflected by these red arcs. So this implicit control flow makes it really difficult to reason about the behavior of the system if we don't do anything special with the code that we're trying to run. And this is especially true if we have things that interact with the environment, like sensors and radios, where going back in time could have a meaningful consequence for some actuation or sensing event that the system is trying to accomplish, which is very common in the types of embedded systems that might be using an energy harvester. Okay, to kind of compound this problem, or at least add another dimension of complexity, these devices often have a mixture of volatile and non-volatile states. So the chipset at the top of the slide and the Capybara energy harvesting platform at the top of the slide both have an embedded, a microcontroller. They're built around a microcontroller that has embedded volatile and non-volatile memory. And both are positioned in those designs as the main memory of the system. And just by accessing a range of addresses, you're accessing non-volatile data, and by accessing some other range, you're accessing volatile data. And in this case, it's FRAM, ferroelectric RAM, which is non-volatile and has good radiation hardness properties. But in general, any non-volatile technology may be built into these kinds of devices. Flash is also fairly common. And so naturally, we know that because of the volatility properties of the memories, some of the state will stick around, the non-volatile state, when there's a failure, and other of the state, the volatile state, goes away. And that includes the registers and maybe data on the stack, things like that. I want to point something out here, and that is that non-volatile state, you're probably thinking this, is useful for doing periodic checkpointing during an execution. And this is a nice kind of first attempt to take the code that we just saw a second ago that's obviously not suitable for running on an intermittent execution and making it a little bit safer to run. So you can see here, if we add a checkpoint at this point, say after the loop, after we've completed the loop, we could checkpoint the volatile state, make a copy in non-volatile state, and then when we boot up after a power failure, we can just reload all the contents of volatile state from the checkpoint. This doesn't actually eliminate the going back in time problem. It just kind of changes the amount of different places to which we may go back in time. So if we pass the checkpoint, then we'll go back in time to from any point to the point of the checkpoint. And if we don't quite make it to the checkpoint, then we'll just go back to the beginning of main. So there's still implicit control flow, and it's still quite difficult to reason about this code, the programmer needs to think for any given statement in the program, is it right or wrong to go back to the beginning of the program or to back to some other checkpoint? And you can imagine checkpoints combined with conditional statements add even more complexity. Then conditionally, we may be going past a checkpoint. So it does, checkpoints are good. They allow you to make progress, even though you're get this going back in time behavior. But I'll show you in a minute that there's actually, they can introduce new kinds of problems that are somewhat subtle and not obvious from just looking at a simple piece of code like this. Okay, so the point is that intermittence is a challenge. Intermittent execution on an energy harvesting system can take code that runs correctly when you have a continuous power supply and make it produce weird, incorrect, bogus results when you have an energy harvesting power supply and the power is intermittent. And that means if we just take our code and deploy it to a bunch of chipsets and we launch them into space and put them in orbit around Enceladus or something, then we're going to have a bunch of new exotic bugs showing up in our code. And this is a claim I'm making now, and I'm going to go through a series of slides next that show you how these bugs, if they crop up in your system, could completely bork your mission. And if you wanted to get nice images processed from satellites of some faraway part of the solar system, you may end up with some crazy thing like this instead. Okay, let's talk about some actual concrete bugs that can happen. This is the section of my talk that I like to call the litany of failures, because it's a whole bunch of different ways that a system can faceplant if you are naive in the way that you add checkpoints and use non-volatile state in an intermittent execution. So again, we have the same program here. I've got a checkpoint on the loop back edge in this code, just to point that out. Another thing is the programmer in this instance, they wised up to this power failure behavior, and they saw that everything was just kind of failing all the time. So they moved these size and buff variables into non-volatile memory. In general, anything that's in this gray color in the slides is indicative of non-volatile memory. So here we have size and buff are stored in non-volatile storage, and everything else is stored wherever the compiler felt like putting it. So we can try and run forward this program on intermittent execution like we saw before. And let's say that we're in loop iteration number 1. We just start randomly in some loop iteration in this execution trace. And we get to this call to append, and we'll go through the statements and append, bump the pointer, and then we'll put an A into the buffer at that point in the buffer. You can see that reflected in the state of the program at the top of the slide here. Normally, I would be tapping on the screen where this was being projected, but unfortunately, we don't have that luxury. Okay, so then we have a power failure, and we've updated our non-volatile state, and we're going to restart again. But you'll notice that we're still in loop iteration 1 because that was part of the checkpoint, and so when we restart it again, we're on loop iteration 1, and we'll go back and execute loop iteration 1 again. But you'll also notice that the state of non-volatile memory just stays updated because we didn't get to the loop, so we didn't sort of record by latching the volatile state that's tracking progress through the loop iterations. We didn't latch that in non-volatile memory anywhere. So we're going to re-execute the same loop iteration again, and memory reflects that we have already completed this loop iteration because the memory is non-volatile. And so this is clearly a problem. If we look at this in terms of control flow, we're kind of stuck in this implicit loop, just going around and around for the first loop iteration. And you don't need to have a lot of creativity to see how this can lead to a really bad situation. We can just run that loop until we get to 11, and then we're still on loop iteration 1, but we're at buffer position 11. No sensible continuous execution trace allows you to access index 11 in this 10-element array. So this is clearly bad news for this program. In fact, something that's interesting about this is this note that I've just highlighted here. The contents of memory depend on where the failure happens. So in a sense, the contents of memory depend on the availability of harvestable energy in the environment, on the capacitor size, and the specific value. Let's say that we're not putting the character A here, but maybe it's some sensor result. the values that get put into memory could depend on sensor outputs. And so there's really a recipe for a security vulnerability here. This is a problem we haven't yet gotten around to looking at, but you could maybe set up a system where you can time where failures happen so that you populate memory with just the right set of values that you can take over and hijack the device or get sensitive biometric information or something like that. In any case, it's at least a problem for the correctness of the program, because when you start accessing out of bounds arrays in an embedded device, you're very close to bricking the device, because you go off the end of this array and you'll just start overwriting non-volatile code memory, and then you have to bring the device home and reflash it from your machine in the lab. So this is the simplest version of how intermittence can lead to problems, even when we have the luxury of checkpointing and we're using non-volatile state to store sensitive program data. The next problem that I'm going to talk about is related to non-termination of a program. And this requires thinking a little bit about the energy cost that the operations in an intermittent system, the energy cost of operations in an intermittent system, like this is a program that I'm showing you here. So what we're doing in this program is we're going into a loop like before, and we're going to call this procedure that's called sense, process, and transmit. That's what's happening over here. And sense, process, and transmit does what it sounds like. We'll collect data from a sensor, process it using some compute kernel, and then transmit it, say, using a LoRaWAN long-range radio or something like that. And in the lab, you may have tested this code out and seen that it worked, but it may be that any of these component computation, sense, process, or transmit, could take a variable amount of energy, and that variable amount of energy may depend on some condition that doesn't exist in your lab setup where you were testing this. So now, if you have the checkpoint on the loop back edge, like we have here, and you start executing and you don't quite make it to the checkpoint because some part of the sense, process, and transmit code is taking more energy than you anticipated before, and so you're exhausting all of the energy before you get to the back edge of the loop, you'll never make progress through this code. You'll be in a sort of what the literature sometimes artfully refers to as a Sisyphean loop, where you'll just keep going around and around trying to complete this task, but because the energy cost to complete this task is more than the total amount of energy that you can store in the energy buffer on the device, the system never makes any progress. And it's a difficult thing to deal with because the energy cost can be unpredictable. It may work when you try it at home, but when you deploy it, then it's broken. So this is a really tricky problem to deal with, and we've got a few different approaches ranging from energy modeling to conservative mechanisms that make few assumptions about the amount of energy available in a device. When we add input-output operations into the system, like using sensors or using radios, things get even hairier. Because now you have a sort of dependence on conditions in the environment being cooperative with what you're doing in your execution. So, for example, if you have a program that needs to sense the temperature and then sense the pressure in the environment, those things, the program should get those things at the same point in time, or else they're not meaningful, because they're meaningful together, but they're not meaningful separately from one another. And so if we have the program that looks like this here, and you'll notice that we have a checkpoint after we use the temperature sensor. So if we collect a checkpoint after we access the temperature sensor and then we have a power failure, we may be in a situation where a very long time passes after we've collected that checkpoint. Once we restore the checkpoint, we'll access the pressure sensor. When we access the pressure sensor, or any other sensor that needs to be consistent with the temperature, we'll get some value that has essentially nothing to do with what the temperature sensor read before the checkpoint because of this very long time passing. So this is an instance where memory becomes inconsistent with the environment in which the device is executing. There are other issues where we can have repeated I/O operations that influence downstream computation that can manipulate non-volatile memory. I am not going to spend time describing this problem in detail, but you can refer to my student Miljana Srbatović's recent work, which was actually about an hour ago in an OOPS main session on dealing with this sort of problem, and coming up with useful and precise formal correctness criteria for avoiding these repeated I/O correctness errors. All right, so now I'm going to talk about the things that we've done in systems to make intermittent execution reliable. And we have, I like to refer to this as the intermittent computing zoo. We have a theme in my lab to give an animal mascot to each of the projects. And my students are very artistic. Some just kind of like doing these little line drawings. One of my students is an award-winning cartoonist. And so we have lots of resources for coming up with nice art artifacts, although we are forced to use clip art in some cases. So anyway, the Intermittent Computing Zoo is a collection of systems that solves different problems in intermittent computing systems at different levels of abstraction. We have systems that are targeted at the programmer, like our work on task-based intermittent execution. We have runtime system support and application system support, like our work on automatic checkpointing and adaptive checkpointing, and running neural network inference on intermittent systems. And we have hardware support and low-level compiler features like energy modeling and new energy system support that I'll talk about later in the talk. So in this talk, I'm going to give a quick kind of overview of Chain, Alpaca, and Coati, which are in a progression of work in task-based intermittent execution models. And then I'm going to briefly touch on some of our hardware work on EDB for debugging and on Capybara for energy management. And then I'll tie everything together by showing you how this fits into an intermittent system that we put into space in 2019. You can download everything that I just showed you from our lab GitHub. If you go to intermittent.systems, there's more information on our publication list and lots of resources. And if you just email me, we're happy to help people get started in intermittent systems. Okay, so task-based intermittent execution is one of the big ideas that cuts across several of the projects that I showed you in the Intermittent Computing Zoo. The idea with task-based intermittent execution is you have some program, you break it up into tasks, and a task is like it's an atomic block in the program. And our system support ensures that it executes atomically. Executing atomically means that you don't have these wild implicit control flow behavior like you had before. The program either atomically executes a task and moves on to the next one and only ever restarts in the beginning of a task. But you never have the case where you're going from an arbitrary point in your code back to some unconstrained other point in the code because of a checkpoint or returning to the beginning of the execution. So the key is that in order to eliminate this implicit control flow and enforce atomicity, we need to selectively checkpoint volatile and non-volatile state at task boundaries. We have a couple of different models for this. The first one goes back a few years to UPSLA in 2016, and it's a model that's called Chain. And the idea here is that to avoid any atomicity problems, we never let a task write a value that it's going to read. And that is a really kind of heavy-handed condition that we put on the task. We have a compiler transformation that enforces it. But by doing this technique that we call static multi-versioning, we separate a task's inputs from its outputs. And by doing that, we can simply re-execute the task from the beginning. All of its inputs will be intact because by construction, those inputs can't be written. The downside of this is that we increase the amount of memory that we consume because any variable that needs to be read, modified, and updated needs to be replicated in the code. This also puts a kind of programming burden on the programmer because they need to think about this new way of manipulating memory. So this solves the problem. Static multi-versioning has very low overhead because doing everything static, there's very little to do at runtime. We don't have to make backup copies of anything. And so we can just sort of zip through the program executing one task then the next using these static copies of the variables. But it's a little bit hard to program, and learning a new memory model is always confusing. So this is Chain, and after Chain, we came up with something that is a kind of variation on the theme that we call Alpaca. Alpaca is another task-based intermittent execution model, and instead of statically multi-versioning everything, we dynamically privatize data. The big idea here is that there's some data that's going to be read and modified in each of these tasks, and we make a backup copy so that if there's a power failure while the task is executing, we can always revert back to the backup copy. So the task will execute using a safe version of the data for the task. And then at the end, after it's accumulated a bunch of updates, it'll commit that to the non-volatile store. and move on to the next task. And we made sure with a little bit of careful engineering that committing that data and moving on to the next task happens safely and atomically despite the presence of power failures. So this, if you're a transactional memory person, probably looks a lot like transactional behavior, where we're doing either redo logging or undo logging. We have an implementation of each of those two options for this system. And the long and short of it is that by doing this privatization of state to a task, we ensure that the task will be safe to execute repeatedly, showing in our paper that you have the property of idempotence. If you re-execute a task again, you always get the same behavior. And that's one of the key requirements for a task-based intermittent execution system. We also have recently added support for, sorry for this animation. Oh, that just slid off the bottom of the slide. I didn't expect that to happen. Okay, so apologies for the clunky animation there, but the last thing related to task-based intermittent execution that I'm going to describe today is Kawadi. And this is a system that allows for a restricted case of concurrency in the presence of a task-based intermittent system. So what I just showed you is that you can break your program up into tasks. We can use privatization or static multi-versioning, and we can make it safe to re-execute those tasks despite the presence of power failures. That avoids many of the problems that I showed earlier in the talk, but it doesn't accommodate interrupts that might happen while your program is executing, like might come from a sensor interrupting your program to update some data structure. And that's very common in these types of embedded systems that we're targeting. Unfortunately, if you have an intermittent system that's executing a series of tasks and you have an interrupt, the interrupt violates the idempotence property that we need for for these task-based systems to work correctly. And so in Kawadi, we take an approach where we allow for interrupts to happen at an arbitrary period of time, an arbitrary point in time. And when the interrupt happens, we use a small and restricted interface to allow interaction for the interrupt handler, to allow interaction with the sensor device or whatever external device triggered the interrupt. That means we can capture the state from the sensor immediately when the sensor fires, but the system, using a combination of runtime and compiler support, serializes the body of the interrupt handler after a task, after a region of the intermittent execution that needs to be atomic to be reliable despite intermittent power. So by splitting the interrupts apart like this and coming up with a principled approach to serializing interrupt handlers and tasks in a system like this, we can have correct interrupt-driven concurrency in an intermittent system. And this was work by my student Emily Ruppel at PLDI in 2019. Okay, I'm running a little short on time, so I'm gonna maybe accelerate through some of what I'm talking about here. The next thing I want to talk about, though, is jumping down a level. So I talked a lot about task-based intermittent execution systems as a way of avoiding some of the correctness and memory semantics trouble that are introduced when you have an intermittent system. We have, if we go down a level of abstraction into the hardware platform, we can look at how a system harvests energy and stores its harvested energy with respect to an application goal. And so the idea here is that we developed an energy storage mechanism that allows reconfiguration dynamically from software at runtime through a combination of low-level software support, compiler support, and custom board-level hardware that we developed. So the sort of simple cartoon version of it is that you have a system that needs to do two kinds of things. In the top case here, you can see that the system is using a single unit of capacitance to store energy. So capacitance is equal to C, and it will fill up the capacitor that has this amount of capacitance, and then it can use that amount of energy when the device hits the lifeline. So if the task for the device is to access a sensor, like the thermometer indicated here, then that doesn't consume very much energy, and so 1 C worth of energy is sufficient. And so the execution will happily proceed through its on and off periods and will collect sensor readings at a regular cadence, and the application works. However, if we try to do something that takes more energy, like activate a radio, and we're using the small the small 1C energy bank that is the premise for this example, then the transmission will never complete. We'll just keep trying and it will fail. We could imagine an alternative reality where we had 2C of capacitance in our energy storage mechanism. And here we would have a longer charging period, which is indicated by this span of the execution. And then after that longer charging period, we can turn on and we have enough energy to successfully complete a radio transmission during that the on period. And so if all we ever wanted to do was transmit from the radio, this would be great. However, if we then want to go and use the sensor, the thermometer, like in the earlier example, we have a very long period where we can't read any sensor values. And then when we do activate the device, we have a whole burst of kind of redundant back-to-back samples from our sensor that might not be all that meaningful. And getting a burst of samples like this, it doesn't give us a lot more information once we've collected one. So these are two different application requirements that are inconsistent with a fixed energy storage mechanism. And they led us to the idea that we need a variable energy storage mechanism that can support either of these modes of operation. Capybara is the system that we built. Like I said, a software compiler, hardware-based system that has banked configurable hardware energy storage. And in the way that this works is you can have a small bank of energy that allows for what we call reactive sensing tasks, like the thermometer on the previous slide, or for what we call atomic tasks, and atomic is unfortunately heavily overloaded word here, like the radio, where we need a long period of activity where we're activating the radio, and that all happens atomically. The system can be reconfigured to have an energy reservoir of either size dynamically from software, and the energy storage can be partitioned so that during a period where we need reactive execution, we can use a sub-bank of the available energy storage, and we can have pre-charged a larger piece of the energy storage so that at some unknown point in the future, we have on reserve a large amount of energy like we might need to activate the radio here. And we call this an asynchronous burst constraint. So the high-level point here is that we have a reconfigurable energy storage system that allows an energy harvesting system to meet a variety of application-level energy requirements through software-based adaptation. Okay, I'm actually going to skip over our work on debugging intermittent systems, although I will say that our system EDB is extremely useful if you're just getting started on building intermittent systems. It gives you a view into an intermittent system that allows you to understand program semantics alongside energy behavior, which is really important for making a system that works correctly. And we can actually integrate it in with a PCB. You can take our design, and if you're doing a custom hardware platform, you can integrate EDB directly into your design, which allows for deploying the debugger directly with the device, which has a lot of benefits because you can do beta testing and get diagnostic information directly from your operating system. I would be happy to talk more about this in the questions at the end. Okay, so now I'm going to talk about space systems, and I'm probably going to spend about only 5 minutes talking about this because a lot of it is actually dependent on the idea that what we're working on is an intermittent system that happens to be deployed in space. So here is an exciting email that I sent about 5 years ago. And this was after we had built the hardware debugger that I just alluded to a second ago. And I had made contact with someone who had some interest in developing chipsat platforms and putting them into low Earth orbit. So the person that I'd been put in touch with was Zach Manchester, who is now faculty in the CMU Robotics Institute. He came by way of Cornell, Harvard, and Stanford or something like that. And I met him when he was just a PhD student. So we've been working together for about 5 years, and he led a mission that was called KickSat-2. And this was the first ever orbital deployment of chipsats. Chipsats are these things that I have been alluding to throughout my talk that look like what you see on your on the slide here, where a whole bunch of them get loaded up inside of a CubeSat, which is that rectangular prism in the center of the screen is about 30 centimeters by 10 centimeters by 10 centimeters. And it's filled up with these chipsets, and each of the chipsets has its own independent power system and sensors and radio and compute capability in the way that I described before. Each of these is essentially an energy harvesting intermittent computer system. So after having met Zach and talking through the requirements of the chipsat mission, we saw a direct connection to the work that we were doing on intermittent systems, and we targeted this chipsat problem as a direct application of intermittent computer system design principles. So on our intermittent chipsat, which we called EDB-SAT in honor of our debugger that we had just finished developing, we have an energy harvesting solar panel array. It's a very small solar panel array. On a good day, you might get 10 milliwatts, but typically you'll get probably between 1 and 5 milliwatts out of that. We have energy storage. We have some features for deployment integration. These are kind of mechanical connection points. We have computing hardware and diagnostics, and there's software loaded on there. And we have computing infrastructure, communication infrastructure. These two not quite attached wires that you see in the corner are taking the place of an antenna that eventually gets soldered onto this board that handles communication downlinking to Earth. And the communication infrastructure is something I'll talk about at the end. So the power system that we integrated is actually it's a variation on the Capybara power system. Rather than having the full configurability of Capybara's software adaptation features, we implemented a version of Capybara that can, based on low-level hardware conditions, switch between two fixed bank sizes, sort of below the software abstraction. Everything else about the power system was the same as we developed in Capybara, and it does support reactivity, atomicity, and asynchronous burst requirements, like I described in my overview of Capybara. So this system has the ability to dynamically reconfigure its power system depending on the demands of the workload and depending on the conditions in which the device is operating. So one of the things that is interesting about this is we have to do this using intermittent energy harvesting system design, because batteries that we want to potentially mount onto one of these chipsets are brittle and they're quite expensive. And in space, you can get down to temperatures as low as -50 degrees Celsius, depending on orbit conditions. And so we found out that all of the batteries that we might use in a system like this, they end up having permanent failures or being very large and infeasibly heavy. A downside to that is that we need to have high quality space-rated solar panels, and they're difficult to come by. And one setback that we had on the way to launching this project was that our solar panel provider sent us a bag of little tiny solar panels, and they just were dead on arrival, and we couldn't get any more of them. The company eventually went out of business, and this was a really big setback. We eventually found a way to get around this problem by getting more of these panels from a different provider and finding a way to make the design work anyway. But the point of me telling you this is that there are strange constraints that come up when you try and launch a system into space, like the fact that your battery will freeze and permanently fail, and a specific type of solar panel is required for the success of the mission. If you don't get it, you don't have a mission. On board, we have a software system, and it runs on this MSP430 microcontroller chip. This is actually a CC430, which has an integrated radio RF stack. And we deployed code that was built using Chain, the system that uses static multi-versioning to keep program state and non-volatile memory safe despite intermittent power failures. And the applications that we implemented were primarily collecting sensor data, doing some archival logging operations, and doing some really rudimentary signal processing to filter out outlier points that came in from the magnetometer and gyro and other sensors that we had on board. Our ultimate goal was to send some of these data back down to Earth, and I'll talk about that momentarily. We integrated EDB. It's actually on the back of the board. You can't see it here. But we have the ability to watch the execution as it unfolds, and we logged when we had power failures. Where were we in the code? Is there a place that's more frequently going to have power failures because of higher activity or higher energy consumption requirements because of, say, accessing sensors? We also had some probe points that allowed us to, from software, collect a trace of energy collected in the energy storage capacitor array over the execution, and streaming this down to Earth would be very helpful for understanding the behavior of one of these devices on orbit. This is information that we just don't have right now, what the power environment for a tiny device like this would be as it orbits Earth. We transmit data to Earth using a simple CDMA scheme. We encoded data with gold codes, which means each of our bits becomes about a kilobit transmitted, and they need to be very long because of the long distances over which we're transmitting and the very low power at which we're transmitting. Our radio's power draw is 30 milliamps at 3.3 volts. So this is really a low power, relatively speaking, a very low power system. And we can do short burst transmissions using the energy that we can store in our capacitor array. And we were actually able to receive data because of the magic of coding theory. We were able to get and decode data on the ground. This this is ironically an email with the subject line "Last Mile Info," December 9th, 2015, 2:35 a.m. We're ready to send hardware. Everything's ready to go. And there's kind of a similar email from 2016. Okay, plugging along. We've been delayed a few times. Later in 2016, okay, we're delayed again. So getting something launched into space isn't simple, and there's a lot of procedural delays, especially when it comes to getting approval to transmit to Earth from space. That just takes a lot of time. We needed to do a full board redesign at one point because one of the mechanical touch points for the deployer didn't line up in our initial design. So luckily we got delayed by several years. We realized that we had to re-engineer our antennas because the initial antennas that we tried to deploy with didn't have the requisite springiness that the antennas needed so that they would actually successfully deploy when we were kicked out of the CubeSat deployer. Eventually, though, we did get deployed. We rode up on one of the Cygnus missions. I don't believe this is an actual image of the Cygnus mission that we were on, but it gives you an idea of the vehicle that we were aboard when we launched. This is a video that I got from Zach. Zach got this from Nanoracks. Nanoracks is the company that manufactures the CubeSat deployer that you see on the right side of the screen. And I think that this video should work. So this was a great moment for our mission, and Zach worked tirelessly to make this mission happen. And that right there is an actual video of the satellite that Zach envisioned and we helped to fill with intermittent energy harvesting chipsats. This is representative of a really exciting moment for this mission because it took about 5 years for the mission to finally deploy. And we got telemetry data after the device was launched from this deployer that it arrived on orbit. After some communications shenanigans, we were able to get signal from this. We were able to get orbit tracking information, which is called a TLE. There was some antenna issues, yet more setbacks, but these were not insurmountable problems. So there was sort of some late night Hail Marying, and Zach was able to, using the Stanford dish, able to make the chipsats deploy from the main CubeSat. This is an image of the equipment that we use to listen to our chipsat after they launched. There are two of these. We very obviously built them ourselves. On the right side of the screen is a handheld Yagi antenna, like you might use to use in an amateur radio setup. And on the left side of the screen is a sort of layer cake of processing components and software-defined radio hardware and amplifiers and analog power conditioning circuits that allows using this antenna, listening to the chipsats that we deployed from the KickSat deployer. There was a moment when we got this message from Zach that he had sent the command to deploy our chipsat from inside of the KickSat to CubeSat. And this is the culmination of the mission right here. And this is only a small piece of the data that we got back. But you can see here that around midnight on March 21st, Alexei Kolin, the student of mine who's now since graduated as a PhD student from my lab, sent me this message. And he marked this one line at the center of this list of numbers, and talk about an anticlimax. So this series of numbers indicates that we were able to successfully decode a packet, and this ED was our identifier byte for the EDB set. You can tell that this was a successfully decoded packet because this number is 0.999 and all the other numbers are only 0.85. So it's a bit of an anticlimax because this is what you get when you launch a space mission. But on the other hand, this was a very exciting moment because we knew that even using that handheld radio listening hardware, we got data back from our chipset platform that we had launched into space. Okay, there's more to the story. I'm going to cut this short here, and I've only got one more thing that I want to do, which is to just give a quick plug for some of the work that we're now doing in my lab on what we refer to as orbital edge computing, where we're trying to increase the compute capability of space-based computer systems and intermittent space-based computer systems in particular. I will not go into any details here because I'm precariously short on time, but I do have what you're seeing on the slide here and what you're seeing in the video is a pocket cube scale satellite. This is also an intermittent computing system. You can see that it has a slightly larger and maybe a little bit more robust array of solar panels. It's mounted on this this white 3D printed piece is not part of the satellite. It looks just like the one in the image here on the screen. And this is a highly capable intermittent computing system that has radio capabilities. It has several embedded computer systems. It has sensors. It has GPS capability. And we're building a collection of these that we intend to launch as a constellation that will cooperatively solve distributed computing problems on orbit, like machine learning on data that we can collect only once we're on orbit, like images of Earth for things like weather analysis and climate analysis, understanding changes over time in coastlines and cities. A lot of really interesting problems that we can solve if we have constellations of sensor-equipped nanosatellites like these ones. So I'm very excited. This is kind of just a plug for our ongoing work in this area. Intermittent systems for space systems is a really exciting area, and I think there's a lot of promise in the types of applications and new techniques, new intermittent computing techniques that we might develop along the way here. I wish we had 2 hours so I could keep talking about this, but I'm going to stop here, and I think we have maybe 15 minutes or so for questions if anyone has questions from Zoom or Clouder or YouTube or wherever. So thank you very much.
Thanks a lot, Brandon. Yeah, if you have questions, you should be able to type them into several different options, and we'll see them. And you can mention whether you want to say your question live in Zoom, or I can ask your question if you've typed it in. In the meantime, I always love hearing about this work. It's obviously very cool work, and I did wonder, you presented the like the intermittent programming model, and is that actually the model that lots and lots of systems actually have? It's just over a much longer time span, like any program that we expect to need to survive any kind of a power failure, or that has any sort of requirement that it needs to run longer, or has a persistence requirement, has sort of the same programming model potentially. So should everyone be using your ideas?
It's a really good question. So there's definitely a relationship between intermittent computing and, in general, problems surrounding persistent memory. One of the big distinctions is that we expect failures to happen very frequently. And in a lot of those systems, failures are an edge case. And so that influences and kind of shapes the choices that you make in how you do recovery and how you might do some things statically or do some things dynamically. So I think that's one of the big distinctions, and you can see this distinction borne out in the design choices we made in Chain. So doing static multi-versioning really inflates your memory footprint by quite a lot. And we saw that as, a downside, but an acceptable one because it eliminated this problem that we had. If you have more time and more energy in a larger scale system, you probably wouldn't make that choice. You might make some other choice, like keeping a log of all the updates to your persistent data structure, or tapping into any of the. There's a lot of really cool work that I love to read about, and any of the work on memory persistency models, or programming persistent memory. So it's really kind of I think it's really in the design approach that you take when you have high frequency power failures and you have very small amounts of energy. Any recovery action could consume half the energy that you have left. And if that's the case, then you won't make very much progress in your execution. Another thing that I think is pertinent here is that a lot of these systems rely heavily on interactions with the external environment. And that can be the case in larger scale persistent memory systems. But when you bring that requirement in and you put this in the context of an embedded system in the way that we have for our intermittent computing work, you see that these kind of requirements for consistency with the external environment, they become front and center, and they need to be part of the programming model and the execution model. And that has a kind of ripple effect down through the layers of the system stack. Those may not exist in other kinds of systems too. If they do, I would actually love to learn about between that from some expert that has been working on large scale persistent memory systems. That'd be, I think, a really interesting connection to make between these two areas.
Mm-hmm. Yeah, it's interesting. I wonder if you're ahead of your time in terms of, like, these are all the problems you're seeing in intermittent computing are also really all problems we should be worried about for all kinds of computing.
I always think when I run into something that says we need atomicity or transactions like semantics, I actually think that we are well behind the time, and we're just catching up to what they knew in the 70s. And I always have that sneaking feeling that that's the case. But I think we're onto something new here just by taking these ideas and working on them in this unusual context. We ran into a lot of new problems that we looked really hard and they didn't have any solutions that we could find.
So I have a question. I forget what SQ means. Alexander, who's in the Zoom, do you want to ask your question live, or am I supposed to ask your question?
Hello. Yeah, thanks for the talk. That was very inspiring.
Oh, thank you for saying
so. SQ is supposed to mean silent question. So but basically the question is self-contained. So I needn't to.
Sure. Yeah, I can talk about these questions. So your first question is there any connection to is there any connection to anytime algorithms? That is a very interesting question. And you've observed something, I think, as an intermediate step that led you to anytime algorithms, and that is the need to think about a trade-off of the amount of energy that you're using to do a computation and the result that you produce. We're looking at this in the context of, we have a computer architecture letters paper on this that came out very recently. It's about a model that is called the phase model for energy efficient computing. It's not specifically about intermittent computing, but it makes a connection between the rate at which you compute, the rate at which you can collect energy, and the result that you produce. And there's a really nice connection between what we're looking at in that work and anytime algorithms, in that if you can stop computing right now and produce a good result, it essentially adds another dimension to our design space. So that's a really nice observation that you've made with that question, and it's an area that I'm really excited about right now. In the context of intermittent systems, especially. I can answer your, I don't know how we want to do this. Do we want to do 2 questions from Alexander, or should we take questions?
It's up to you. I know you have a time constraint, so it's entirely up to you.
Yeah, I'm happy to go a few minutes over if there are questions to answer. Our recent NVRAM data structure and algorithms, so this is kind of related to what I was saying to Mike a second ago. The question is whether recent advances in non-volatile data structure, persistent memory models, and algorithms for non-volatile memory, are they relevant? And I think the answer is that some are and some aren't. And I think that there's a fairly complex set of assumptions that gets built into any system with non-volatile memory and some set of application requirements. And in our case, energy drives everything. These other non-specifically, it's hard to say whether a system is relevant to an intermittent system. But if we have a requirement that the system not consume too much energy to provide a strong guarantee of correctness, that may make some options more appealing and may make other options less appealing. And we have, tried to find the balance in our work here of using just enough energy that we have a useful and reasonably performant system. Also, as I said a second ago, the relationship between the program execution and interactions with the environment through I/O, like using sensors and radios, it adds another dimension that is not typically handled by most of the work, non-volatile data structures and algorithms. And I think that adds a really kind of interesting dimension to it, because you have another source of what, from the program perspective, looks like non-determinism. You have values sort of appearing out of nowhere when you go and access the sensor. And if you think about the consistency requirements on an execution that has those kinds of values in it, you end up with some kind of interesting conclusions in how you design your system. And that's a problem we're actively looking at right now. So I think there's a relationship, yes. I think that no solution directly drops in and solves this problem, but I think that they're definitely in a related design space.
So David Luhals has a question.